welcome to the lesson on hybridization. All right, so you mustn't get overly hung up on how it happens or why it happens. All right, it's just the way that we model the geometry. That's all you've got to know. Nothing more than that. All right. Anyway, so now, yeah, turn your microphone off now, dear. I don't want to hear you coughing in the background. So these are known as Sp2 hybrids. So they're two S3. These are the hybrid orbitals. Hybrid orbitals. Now, what's the whole idea of this then? Well, this model here about hybridization is just to explain the geometry, okay? Because if you look at this model here, it would mean carbon can make two bonds, which it doesn't, does it? That must be wrong. Look here, it can make four bonds. So this is much better, all right? But this one, if it was this one, the bonds would be, and I think I mentioned this in class, would be different lengths. Different lengths. And they're not. So it can't be this model either, can it? So we come up to, oh, well, what happens then? Let's think about a mixing of bonds, and we get this model, this hybridization. Now we get four bonds, which is good, and we get four bonds, and they're all the same length, which is good. So that works and that works, okay? But it's a model. You shouldn't overthink it, okay? It's just a way we can explain the geometry of compounds. All right. It's a very complicated model, but that's all it is. It's a model to help us understand things. All right. So there we go. So we got these four hybrid orbitals there. And if we look at this now, okay, we've got a carbon. Let's draw a carbon. All right, there's a carbon atom. Okay, and now we've got four electrons, 1, 2, 3, 4, on the outer layer, if you like, of carbon. Okay, so they're going to form a tetrahedral shape, aren't they? Okay, we're going to get a bond up there, a bond there, a bond out of the board, and a bond into the board. Okay, does that make sense? Ludzi's joined. Hello, Ludzi. All right, Amantli, is that a bit better? We're not quite there yet, but is that a little bit better?
Yes, sir.
Oh, guys, you know what you mustn't do? You mustn't unmic because it scares the life out of me. Just put it in the chat. I don't have to hear your voices. Trust me, I hear enough of them all day long. All right, if you want if you want to answer, just put it in the chat. Okay. God, I should turn the microphone off. Amanda, yeah. Well, don't even your chats are shouting, aren't they, with the capitalization? All right. So this is carbon now with the four hybrid orbitals. This part is fine. Thank you very much. All right. So now let's draw the hybrid orbitals. Okay, around my carbon. So where's my carbon? There's my carbon. A nice carbon. Okay, and the good thing about these hybrid orbitals, they're going to take the orientation that we've just talked about. They're going to be tetrahedrally arranged around the carbon. Okay, so that's what I've tried to draw there. Let me draw the orbitals on. This is one of the Sp3s. Oh, that's not good, is it? It always does that. There's another Sp3. Oh, why does it do that? There's another Sp3. And there's another Sp3 behind. Okay, how many electrons are in here? They're there, aren't they? These four are the ones I'm looking at. Okay, so 1, 2, 3, 4. What are these orbitals? Well, first of all, they're atomic orbitals. All of them are atomic orbitals. Okay, they're not S's, are they? They're not P's. They're Sp3s. They're a mixture of 1s and 3 P's. Okay, now, well, when would carbon form this shape? When the carbon forms any tetrahedral shape. When it forms any tetrahedral shape. In other words, when carbon has 4 bonds, all right, in a tetrahedral. Carbon always forms 4 bonds, but it doesn't have to be in a tetrahedral, does it? So, as an example, I think a good example is methane for that. Okay, now what have I got to stick on the end of my orbital? I've got to put my 4 hydrogens, haven't I? Okay, let me put my electrons in there. 1, 1, 1, 1. Let me do the nuclei. Okay. Now, excuse me. Right. Now, this stage, what I've drawn here, is analogous to when I did chlorine in the lesson. I did chlorine. I drew the orbitals. I draw the axis there. I said this is a p orbital, and this is a p orbital. And what happens is these two merge, and we get this. That's from one. That's from another. Okay, so how many's in here? There's one electron there, one electron here. These are atomic orbitals, aren't they? Does anyone in the chat tell me what the name of these atomic orbitals are from here in chlorine? What's the name of those atomic orbitals? Oh God, now no one's going to type anything after a month has been shouting at us. What are those atomic orbitals called? Anyone? Oh, maybe you can unmic then, if you prefer it. Someone unmic and then tell me what are those atomic orbitals called. Maybe my internet's gone off and I just don't know. What are the atomic orbitals called? Yeah, they have a name. Yeah, what type of atomic orbitals are they? They're P's, aren't they? No. What about that? If it's sigma is a molecular orbital, isn't it? So do we understand that in the case of chlorine here, when we were doing molecular orbitals, before I did the molecular orbitals, I draw two p orbitals. Okay, and this is 1p. Let's say it's the px, and this is the px. Remember that? So these orbitals here, these two, are p orbitals. One's a px and one's a px. And look, I've just shown them overlapping. Do you get that? Are we good there? What happens? What's the next stage of this? Well, now I draw them merging, don't I? And I kind of draw this shape. Okay, this merges to form this. How many electrons are in this orbital here? There's two. What type of orbital is this down the bottom there? Anyone know? Type of orbital down the bottom. It is a molecular, well done. It is a molecular orbital. And, oh, well done, Amantle, you nearly spelled it right. This is a molecular orbital. And because of the way we talked about these things, this is a sigma molecular orbital or a sigma bond. Do we understand this area on the right of the board? Are we okay with this area here? Do we get that? Yes, Laurel gets it. What about Amantle? She's the one that asked. Tammy gets it. What about a monthly? Monthly gets it. Yeah. Now, where are we here then? Which part is this? Well, this part here is analogous to this part. I've drawn the atomic orbitals, but I haven't merged them yet. Does that make sense? Okay. I hope that makes sense. Lucy says yes, but I don't know what she said yes to. Maybe it was the previous bit. So I've drawn the atomic orbitals, but now I'm going to merge them. So at the moment, all I've drawn is the atomic orbitals, and now I'm going to merge them. So let's merge them. Well, that's my original carbon in the middle. Okay, so this and this merge together to make this. Oh, stop doing that. Are we okay with that? Now there's the hydrogen. It forms a new orbital, and this one is a molecular orbital. This is a molecular orbital. And what type of molecular orbital is it? It's a sigma bond as well, because it has rotational symmetry. Or if you like, it's end-on overlap, isn't it? Yeah? How many electrons are in this guy? Well, there's two. One from the sp3 and one from the 1s. And that's it. Are we good with that? Again in the chat. Now, while I'm waiting for you guys to say something, I'm going to draw my lines. Now, why am I drawing these lines? Just to give me an idea of the geometry. I just want to make it beautiful. I'm waiting in the chat. Donna, I don't know what the yes means. It means you get it, does it? All right. And then, well, this one. There's another one. And, oh, that's ugly, that last one. This one. And, oh, that's not good. It snaps the grid, as they say, and this one. And there's a hydrogen there, hydrogen there, hydrogen there. H, H, H. How many electrons are in each of these new molecular orbitals? There are 2. They're all sigma bonds. All of them are sigma. Are we good with that? Oh, please repeat what, Laurel? I don't know what bit you meant me to repeat, I'm afraid. Laurel, you can put the mic on if it's going to be easier. What bit? Laurel? You got it. Okay, cool. All right, so that's methane. So let's. I think Amantha is the one that was moaning about this, so I hope she's a bit better. But again, you're overthinking this, guys. It's a lot easier than you think. All right, so let's draw a methane. Okay, let's draw. There's a methane. This is how we draw it, isn't it? When we draw it on a two-dimensional thing. Now, what can we say? Well, this is a bond. What type of bond? It's a sigma bond. By the way, all single bonds are sigma bonds. So this must be a sigma bond. This is a sigma as well. In fact, they're all sigma. All of these are sigma. Okay. How are they made? How did we make them? Well, all bonds are overlaps of atomic orbitals to give us molecular orbitals. Yeah. So what bonds here, what bonds in each of these bonds, in the CH bonds, they're all sigma, that's something we can agree on. All right. But what atomic orbitals overlapped to make this sigma bond? Anyone want to tell me? What orbitals overlap? Now, while you're thinking about that, I'm going to dig around on my computer to see. Yeah, 1s, not a P, not a P, dear. All right, I think you still perhaps don't quite get it. I'm digging around for some multiple choices because I know there's some multiple choices with this sort of rubbish on. Okay, you think I'm not looking at the chat now. You can write anything you want for now. I'm looking at some past papers. All right, but I can't see the chat at the moment. I'm looking forward to see if I can get a nice example. And unfortunately, typically, there's not many questions yet on this. Oh, that's a bit nasty. Oh no, you can't do that one. All right, none there. None in summer 19. Okay, so let's have a look at this one. Oh, there's a nice one. Yeah, I can show you that one. That's quite a nice one. All right. So, let's put that up there. All right. Yes, Laura's right. I'm looking. Let's have a look. Let me go back. All right. Laura originally said, well, that's not so. We need 2 things, don't we? S and a P. That's not right, Amantha. Amantha says S and a P. It's not an S and a P, dear. SP3, S and SP3. That's right, Tammy. Basadi is right. Amantha. You don't say P, you say SP3. Yes, dear. 1S and SP3. Laurel keeps on saying the same thing. But what made this bond here? What made it? Let's go over here and see what made it. Well, it was an over. Oh, sorry, I should go over here, shouldn't I? What atomical orbitals made it? Well, it was between the S and the S. Oh, that's horrible. And the SP3, wasn't it? SP3. So this was made from an overlap of an SP3 and an S orbital. And that's it. That's all I want you to get from this. Okay, I promise you that's it. Right, now let me get the question. I don't know, I haven't looked at the question. I haven't looked at the answer, but I just saw a nice picture and I want to use it. So I'm going to give you a picture, see if you get this. All right, where's my thing? Edit, file, is it on edit? I think it's edit. They've changed Adobe a little bit. Okay. All right. Oopsie daisy. See if we get this. What's the answer here? Can you all see that? Can you see the picture? All right. How the bonds would look. Okay, I'll do that in a minute, Laurel. All right. A sigma bond is made between 2 carbon atoms in a molecule of ethene. All right. Which diagram shows the orbital overlap that occurs? What do you think the answer is there? I think so as well, Basadi. I think it's C. Carbon. Well, interestingly, the sigma bonds in ethene. Okay, what's it now? Without doing any work, Basadi's is right. Do we all understand Basadi's is right? But let's have a look at her. Let's have a look at why she said that. She's exactly right. Okay, right. Now let's have a look at ethene. There's ethene. Now we've done the hybridization. Okay, now let's dig this apart. There's a CH bond, there's a CC bond, and there's another CC bond. All right, what type of, let's try and draw a table. What molecular orbitals are formed in the CH bond? Someone tell me that. I don't think you can. These are going to be Greek letters, so you have to give the Latin interpretation. Well done, Basadi. It's a sigma. What about one of the CCs in ethene? This guy is ethene. One of the CCs? That's right, one of them is a pi. What about the other one? Sigma event. Oh, and sigma. Yeah, so Basadi got it as well. It's a sigma. In other words, all of these are sigmas. One of these is a sigma, and one of these is a pi. Yes? Now, gets a little bit tricky now, but let's see. Okay. What was the hybridization around this carbon? And this carbon's the same thing. What's the hybridization? Hybridization. Okay, what is the hybridization? Yes, Vasani, I'm one of the bonds. what what does that mean, dear? Are you recording? I am recording. Didn't I say? Didn't you hear the thing? Hold on, Laurel. No, 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 dear. You got to be careful. That's not what I asked. What's the hybridization here on this bond around these carbons? Anyone? What's the hybridization? No, no, the hybridization. There's three things you could say. You could say it's sp3, it's sp2, or it's sp. Amanthe, why do you say sp3? Do you know why you're saying that? All right, then let's stop. Let's not answer my question yet. Okay. Now, if it's sp3, yes, no, yeah, amazingly, you're all getting it wrong. If it's sp3, add up the indices in sp3. If I add up the indices, what do you get? Adding the indices in sp3. 4. That's right. sp2 gives us 3. sp gives us 2. Yes? If it's sp3, whoopsie daisy. If it's sp3, it must be tetrahedral with 4 bond directions. If it's sp2, it must be trigonal planar with 3 bond directions. 4 bond directions is going to give us tetrahedral. 3 bonding direction is going to give us trigonal, whoopsie daisy, that's gone very wrong. Trigonal planar. And 2 electron directions is going to give us linear. Remember that? So if it's that, it's that. So if you see carbon like, let's have a look, like this in tetrahedral, all of these bonds, they must be sp3s. Because sp3 means tetrahedral, and tetrahedral means sp3. What are they here? Well, this must be, there's 3 electron directions only, and therefore that must be sp2, trigonal planar. And here there's 2 electron directions. These must be sp. Yes? Are we good with that? Are we good? We've done the ethene diagram in class, so I don't really want to do the ethene again. I could do if you want me to. All right, we could do ethene. Now, Amantle wanted us to do methane, but I could do ethene if you want. Do it again. Oh, bum. All right, we're going to have to edit that bum out, aren't we? All right, let's do ethene. All right. So, first of all, what are we going to start with? You are all taking this too seriously, though. Seriously. All right, 1s2, 2s2, 2 1 2. All right. I thought each. Hold on. No, I don't know, Laura. We'll see. I thought each SP adds up to 3. No, 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 no. That's not why it's called SP3. This is 1s2, 2s2, 2p. All right, 2p2. What's the first thing that happens? Try and keep up with me. Promotion. Okay, so this becomes this. 1, 2, 3, and 1 gets promoted. This nothing happens there. 1 happens there. Okay, and that's promotion. This is the S. These are the P's, and this is the 1s. 1s2, 2s1 now, isn't it? 2p3. All right. What's the next thing that happens? Next thing that happens is the mixing, hybridization. Okay. Now, there we are. Now, when we first did it, Amantha, you've got help here. When we first did it, how many well, there was 1s. How many P's did it mix with? How many P's did the first one mix with when we did methane? Let me go up because I don't think anyone's going to answer that of their own free will. Here we go. Look at this. Can you see 1s merged with 3 P's? Yes? So what would you call that kind of hybridization? S, because there's 1s, to the power of 1, P, but there's 3 P's, to the power of 3. So that kind of hybridization is called sp3. How many electrons are involved in sp3 hybridization? How many electrons? Someone answer that? Well done, Body Bunny. There's 4. Okay, there's 4. We're looking at it now, aren't we? There's 4 there, sp3. What geometry will it have? What geometry will the carbon have if it's sp3 hybridized? Well, there's 4 electron directions around the carbon, so the geometry must be tetrahedral. Well done. Are we all good with that? Can we assume we're good with the methane model? Well done, everyone. Okay, now I'm going to move this up and we're going to go down. But now, like, oopsie daisy, what happened there? Oh dear, I hope that didn't mess anything up. Now, I don't want my S to merge with 3 P's. I want my S to merge with 2 P's. Are we good with that? So if my S merges with 2 P's, there's the unused P. This is 2p, but the S is merging with 2p's. So how many electrons will be involved in this kind of bonding? It will be 1s, whoops, wrong color, 1s and 2p's. Yes, exactly, Body Bunny. Yeah, and now we have, where are we? There we go. We have 1, 2, 3. This hasn't hybridized. We have unused this one. This is our 1s2. But now the S has merged with 2p. So what are these hybrid orbitals called? What are these ones called? Anyone? Oh, what's that? I've got a message. Exactly, sp2, because it's 1s and 2p's. S to the power of 1, p to the power of 2. These are these are sp2 orbitals, yes? Are we all good with that before we go on? Are we all good? Body Bunny gets it. Basadi gets it. A monthly, I don't know about a monthly, what that means. A monthly, what does that mean? A monthly gets it. Donna can't spell. Laurel, oh, Laurel! From where? From where do you... Oh, I'm looking out the window. From where, Laurel? Didn't you say that before? From where? From the methane? I do, but I don't, but I do. Where does the unused be? We haven't, we'll see, dear. Just the hybridization part. Amantha, we'll see. Stop jumping ahead. All right. So we've got these 3 hybrid and the unused P. Okay. All right. So let's start again. Okay. Oh, well, Amantha, Right, so promotion we're good. Hybridization. What's the mixing now? Now, when we did the first mixing for sp3, what did we mix together to make sp3? We mixed an S, a P, a P, and a P. Yes? Hence sp3. What are we going to mix now for making ethene? S, we're going to make sp2. So that's going to be a mixture of an S, a P, and a P. Yes? Are we good with that, all of us? Yes? Yes, no, maybe? All right, well, no, Pomolo says no now. Oh my God. Right, I'm going to plow on and see if things fall into place. All right, so now we've got the Sp2 hybrid orbitals and the unused 2p. We haven't used this yet. How many electrons are involved in Sp2 hybridization? Someone write that down for me. In the chat. Well done, Amanda. Three. There's three. So what would the geometry be around an Sp2? Oh, no, no one wants to answer that one. What's the geometry around an sp2? Yeah, trigonal planar, because there's three electron directions. But Ola, you do get it. Okay, there's three electron directions. Remember we did this. The thing about me doing hybridization is we did it very soon after we did molecular geometry. And I honestly don't think the molecular geometry sunk into your heads. I'm asking you to remember things from molecular geometry that you kind of didn't put a lot of effort into in your brains. Okay? And now I'm asking you to remember stuff that you never really used in the first place, if that makes any sense at all. All right, so now we have three electron directions because it's sp2. Okay, so as everyone's saying, it's trigonal. So how am I going to draw that? Well, it's carbon. Now I'm going to do what I did in class because there's three electron directions. I'm going to draw a nice triangle around it. There you go. I don't want that triangle, I want that one. Okay, and this is one. They're all in the same plane. Okay. Now, do you understand that? That's all in the same plane. All right, and it is around this carbon. It is trigonal planar. It's trigonal planar around that carbon. Okay, it's not very helpful, this diagram, is it? So what I'm going to do is I'm going to look at it from the top. So let's look at the carbon from the top. It would look like this. It would be beautifully. It would be like that from the top, but it's in a plane. That's in a plane, but we're looking at it from the top. Okay, if I were to draw a bond angle here, it would be beautiful 120 because it's 120 here. All right, now there's one, and the carbon there is sp2 hybridized. So that means it has three sp2 atomic orbitals coming out of it. So let's draw them. One, oh, that's ugly, isn't it? Two. Oopsie daisy, stop doing that. And three. And all of these are sp2, and I'm going to put an electron in each of them. One, two, three. Are we good with that? Do we understand that? I'm going to go off into the internet while you're seeing if you understand that. I'm going to do ethene hybridization. Hybrid. I want a nice picture. Okay, if I can get one. Bum, 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 bum. Oh, gosh, you get so much nice stuff on the internet these days. You really do, seriously. All right, so while I don't know what you're doing, but you're going to be doing stuff. Hold on, move that over there. I've got a lovely picture for you. Well, I think it's a nice picture. Woo, that's lovely. Right, I'm going to save that as that. Okay, there we go. All right. So get rid of this. Go back to you guys. A month is good. All right. So we're looking at it from top. I'm going to show you something beautiful in a minute. The picture I've just found. Okay. So how am I going to make this bit more believable for you? I'm going to draw a compound. So I'm going to draw another C here, exactly the same. Okay. And I'm going to draw these. This one is exactly the same. Oh, stop doing that. All right, there and there and there. Okay, I'm going to put the electrons in here. What are all of these orbitals I've shown so far? Hold on, Laurel. What determines if we come up with that, or that? It's the hybridization that it undergoes. That will determine which shape it is. So, what orbitals have I drawn only at the moment? I've only drawn, well done. I've only drawn sp2s. They're all sp2s. This is an sp2, and this is an sp2. They're all sp2s. Okay. Now, what am I going to draw in the end? Well, I'm going to draw my hydrogens now. There they are. Okay. And now, as you all know, there's one electron in each of these. One, 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 one. All of these I've drawn so far are atomic orbitals. And now I'm going to merge these to make my molecular orbitals. Okay, so let's do this. Let's merge them. There's a C. This is going to form a nice sigma bond there. There's another C. This one is going to form a nice sigma bond up there. This one is going to form a nice sigma bond down there. This one is going to form a nice sigma bond up there. And this is going to form a nice one down there. All right, and how many electrons are in each of these? There's 2 electrons. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And what have I drawn so far? I've drawn this. And so far, they're all sigma bonds. Sigma, 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 sigma. Okay, and there we are. Okay, so far so good. And the bond angle here, and don't forget there's a hydrogen there at the end. We don't. It's kind of been absorbed by the bonding. Okay, now, are we good with that? So we've kind of drawn the skeleton, a sigma skeleton it's called. All right, so we've drawn the skeleton. Are we all good? Or is everyone left? Are we all good? Amanda's got. Amanda, is it just you? Right now, Laurel's got a thumbs up. Well done. Right now, we've just drawn that. Now, what I was going to go up for some reason. I can't remember. I'm going to go up and see if I remember. Why am I going up? Oh, I can't remember now. Oh, yes. Now, do you remember what everyone was? Oh, Bonolo, what dear? What happens to the Zoom? That's what we're going to do now. You've got no patience. That's why I moved the paper up. Remember the unused 2p. Remember that one. Bonolo. Do you remember that? Yes? There it is. And now we're going to use it, aren't we? Now, what orientation is that in? Now, let's do my carbon, hydrogen. I hope this drawing makes sense. All of this, ladies and gentlemen, all of this, and I haven't drawn it very well, but all of that is in the same plane. Can you kind of get that impression from that silly little rectangle I've drawn, the one in yellow? I'm trying to get you to appreciate that that's in the same plane. Are we good with that? It's in the same plane because it's sp2 hybridized and it's trigonal planar. So it's all in the same plane. Everything's in the same plane. Yeah? So would anyone like to tell me where is this unused p orbital? Where is it? Anyone? No one? That's right, out of the plane. That's right. And now it's above the plane and below the plane. Yes? The ball. Is eaten by the Cookie Monster. Very good. Oh, who's this? Tandy wants to come in. I don't know why. Hold on, let me try and get Tandy. There we are. Welcome, Tandy. Hope you're okay. Definitely not in the same plane. Yeah, exactly. And what is going to happen? Well, these are going to merge with each other, aren't they? And these go away. Google keeps telling me things. Yes. And we're going to get a pi bond above and below the plane. And this is going to have 2 electrons in. All right. And it's a pi bond. Okay, so the last one here is a pi. Are we good with that? I think we're kind of good. So let me see how your understanding is. All right. So here is ethene. Okay, and what bonds are in ethene? Well, there's a bunch of CHs. They're all the same. There's a CC, and then there's a CC. Okay, first of all, what are the molecular orbitals in all the CHs? All the CHs are sigma. Yes? What are the molecular orbitals in one of the CCs? Well, according to this picture here, one of them is a sigma, and the other one is a pi. Are we good? Well done, Bodhivana. Yes? Now, what made them, though? What's the overlap? The overlap to make the CHs was between what and what? Nitrogen has rotational symmetry. What? No, it doesn't, because there's pi bonds. If you look at it along the bond axis, it doesn't have rotational symmetry. All right. So what's the overlap here to make a CH bond? Anyone want to tell me? What made the CH bond? What's the overlap? What orbitals made that? Well done. Who's that? Laurel, yes. It's an S and an sp2. Well done, Abote, as well. What made the sigma bond of the CC? What overlapped there to make this one? Anyone? Yes, Laurel again. And sp2 is well done, everyone. I think we're getting there now. sp2, sp2. And what made the pi bond of the CC? Well done, PP. Excellent. Bodhivana, well done. PP. Are we good? So now, okay, so let's have a look at this one in more detail. Let's have a look at this one in detail. It was an sp2 overlapping with an sp2. Okay, now watch this, and I'm going to try my best here. Oh, that's not bad actually for me. Now, and be careful of this answer. What am I drawing here? What are these atomic orbitals I'm drawing here? Don't be fooled by this. Well done, Amantle. Well done, Laura, as well. These are P's. So this is a P side-on overlap, and this will give us a sigma bond. Are we good? Well done. I didn't think you'd get that, but I was really trying to draw nicely. So this is a PP overlap to give me a sigma, yes? What would this look like then? Well, if you remember the lesson, an sp2 looks like this. It's got a bigger lobe and a smaller lobe. So this one would look something like this, a bigger lobe and a smaller lobe. So what am I trying to draw here? What's the overlap here? I'm trying to draw what? Anyone? Basadi, I haven't heard from you for a long time, and you were... Yeah, I'm trying to draw an sp2 overlap. This is a P, and this is an sp2. Okay, there's an electron in there, electron in there, electron in there, electron in there. Now, if I overlap to P and a P here, what type of molecular orbital would I get? If I overlap to P and a P, what type of molecular orbital would I get? Actually, I've given it away there. It's sigma. If I overlapped an sp2 and an sp2 like this, what kind of molecular orbital would I get? Don't be shy, try and get this one. Again, it's a sigma. Are we good? Is everyone good? Apart from Laurel, is everyone else good? Yeah, okay. Now, this is the last thing we're going to do today. Basadi, well done. We're going to go back up to the picture. Look at this. We've done a lot of stuff. Look at all this, my word. Interesting. God, we did do a lot of stuff. Now, let's have a look at the picture. A single sigma bond, this one, A sigma bond is made between two carbon atoms in a molecule of ethene. Which one shows the overlap? Now, first of all, what does A show? What does A show? The overlap of what and what? Oh, no, it's not a P and a P. Yes, it's an S and an S. And what type of bonds would be formed if an S and an S overlapped? Well done, sigma. What does B show? Overlap of what and a what? An S and a P. Well done. And what type of bonds would be formed? Sigma again. Well done. Now look at C. What's C showing? What are those two orbitals? Not SP, not SP, guys. In this case, it's Sp2, Sp2, because it's ethene, isn't it? And what type of bonds would be formed? Well done about this, sigma. And what's D showing us? A P and a P, that's right. And what type of bond would be formed? Pi, that's right. So now read the question and tell me the answer to the question. And the answer is C, because it's Sp2, Sp2 overlap to form the sigma bonds. Well done, Amantle. Well done, Abutle. Well done, Manolo. Now I'm going to change one thing in the question, and you're going to get a different answer. I'm going to get rid of this sigma, and I'm going to say pi. What's the answer now? Well done, Manolo. Well done. It is indeed D, because that's how the pi bond forms in ethene. Now, ladies and gentlemen, we've been here an hour now, but believe it or not, I think we've done quite a lot of stuff. It's very technical, this, isn't it? And look at the question. The question looks very easy, and it's very easy if you understand the question. But you've got to do quite a lot of in-depth chemistry to get to that, to get to the understanding of why the answer is C. But are we happier than we started out? That's the main thing. Let me turn off the